In this lesson, we'll delve deeper into the topic of materials, considering them as a large family in which each element is defined by its own unique characteristics and properties. But what do we really mean when we talk about materials? From a practical point of view, they are the element that allows the project designer's idea to take shape, a sort of bridge between the world of ideas and the reality of the product. Without materials, ideas remain just ideas. But if we choose them consciously, we can turn an idea into a successful product that combines aesthetics, functionality, and innovation. In this lesson, we'll explore the major families of materials, metals, polymers, ceramics, and then composites and others as well. We'll go beyond their simple classification and connect them to their properties, because what we're looking for isn't just a material, but rather a set of characteristics capable of meeting the requirements of a project, a property profile. To help us navigate the various materials used in engineering, it's useful to classify them into different families. Metals, polymers or plastics, elastomers or rubbers, ceramics, glass, and natural materials. And finally, there's a very broad family of hybrid materials, whose components are made by assembling different materials together, as in the case of fiber-reinforced materials or foams. Each material family groups together elements with similar characteristics, chemical and physical properties, processing methods, and typical uses. Let's take a closer look at them, starting with the materials most traditionally used in engineering. Let's start with metallic materials. They are widely used for structural applications, mechanical components, and electrical systems. They are rigid, strong, and excellent conductors of heat and electricity. Their properties can be improved with alloys or heat treatments. However, they are heavy and, if not protected, they rust. Now let's move on to a broad family that, since the 1950s, has revolutionized many fields of engineering, from consumer goods to electronics and automotive. We're talking about polymers, commonly known as plastics, and elastomeric materials, that is, rubbers. Polymers are materials that are lightweight, easy to work with, and generally inexpensive. Although they are less rigid and less strong than metals, they stand out for their remarkable versatility. Their behavior changes significantly with temperature. At low temperatures, they tend to become rigid and sometimes brittle, while at high temperatures, they become more flexible. Many polymers even lose their properties once the temperature goes above 150 degrees Celsius. Closely related to polymers, we find elastomers, more commonly known as rubbers. They share many of the properties of plastics, but are distinguished by unique characteristics. They are extremely flexible and capable of significant deformation, then quickly return to their original shape. Now let's look at a family of materials widely used in the construction sector, but also in advanced fields such as aeronautics and aerospace, chemical engineering, and pharmaceuticals. We are talking about ceramic materials and glass. The former are distinguished by their high hardness, resistance to wear, and to high temperatures. They are also characterized by remarkable stiffness. However, they have a significant drawback. They are brittle and often heavy. The materials in the second family are chemically similar to ceramics, but are distinguished by a unique feature: transparency combined with chemical resistance. They are ideal in the construction sector, where it's necessary to let light through, but these materials too are brittle and delicate. Now let's talk about natural materials. They have accompanied humanity since its very beginnings, but even today they are fundamental for eco-sustainable design and for certain unmatched qualities in many fields. The family of natural materials is very broad and includes natural fibers. Cotton, leather, straw, but in the construction field it is mainly represented by wood. Wood is valued for its strength, lightness, insulating capacity, and low environmental impact. However, it must be carefully selected and treated, as it is sensitive to humidity and temperature changes. Finally, there is a large family obtained by combining different materials together, thus creating unique properties that are better than those of the original materials. Let's talk about hybrid materials, such as composite materials and foams. Among these, the former are the most representative materials of this family. They manage to combine high stiffness and strength with great lightness, although they are often among the most expensive. But as we were saying, when a project designer chooses a material, they're not just looking for a name, but for a specific profile of properties. In other words, the name of the material is just a label behind which lies a certain set of characteristics. Each of them can be described as a multidimensional system, a set of properties that define the material's behavior in different situations. Let's look at the most important among those for general use, such as density, which describes the weight of the material in relation to its volume. And this is fundamental in designs aimed at reducing weight or costs. Density and cost are key parameters for the economic feasibility of a project. Now let's move on to mechanical properties, which are essential for engineering design. The Young's modulus defines the stiffness of the material, that is, the material's ability to resist a force that tries to deform it. Yield strength defines the force beyond which the material deforms permanently, while tensile strength is the force beyond which the material breaks. Hardness defines the material's ability to resist scratches and wear. Finally, fracture toughness is a fundamental parameter for describing how well a material can resist sudden breakage due to internal defects. In certain types of applications, thermal properties are also essential. The maximum and minimum operating temperatures help us understand whether a material can function within a specific temperature range. Thermal conductivity tells us how quickly a material allows heat to flow through it. The coefficient of thermal expansion, on the other hand, describes how much a material deforms when it is heated or cooled. Finally, specific heat capacity tells us how much energy is needed to heat up or cool down a material. And then there are many other properties you can list, for example the electrical properties, which describe whether a material is a good insulator or a good conductor. The optical properties, which describe the interactions between a material and light, whether it filters, reflects, or completely transmits it. The environmental resistance, that tells us how well a material withstands corrosion, humidity, and solvents. The properties related to sustainability, which measure the impact a material has in terms of energy and CO2 emissions on the surrounding environment. And many, many more. These properties can become absolutely crucial depending on the type of design you need to follow. In this lesson, we learned that materials are the link between the project designer's idea and the actual object, and they determine a product's characteristics, its appearance, how it works, how long it lasts, and how sustainable it is. Materials are divided into families, each with specific characteristics and particular uses. When a designer chooses a material, they're not just picking a name, but a precise combination of properties: general, mechanical, thermal, electrical, optical, and so on. To make a good choice, it's important to know the families of materials and start seeing them as multidimensional systems, each different from the other precisely because of the set of properties they offer.